For 1.3, our simplifying radicals practice, which required, in order for some setup to talk about simplifying radicals, we had to talk about this rule for multiplying radicals. And just as a quick reminder, we're multiplying two radicals that have the same index. We just multiply the two radicands together. And if they have coefficients, the coefficients get multiplied together as well. Okay. So I'm probably going to start relatively quickly, and I'm going to slow down as these things get a little bit more in-depth. So first, this is just a straight-up multiplying radicals question. It becomes really the root of 5 times 3, which is just root 15. And I might ask myself, can 15 be simplified in some way? And to do that, I'm actually going to write all my perfect squares along this margin. 6 sixes is 36, 49, 64, 81, 100, 121, 144, and hopefully that's all the perfect squares we're going to need. I'm also going to write down the perfect cubes over here. So 1, 8, 27, 64, 125, 216, and again, hopefully that's all we'll need there. And so then I might check and say, well, do either of these guys, are any of these perfect squares a factor of 15? And the answer is no. So that leaves us with that step done. Okay, for this one, we have a little coefficient here, a -1. It doesn't really get involved because what we're doing is multiplying 3 by 7, which together gives us negative root 21. And again, these perfect squares aren't factors of 21, the exception, of course, being 1. All right, so then we'll multiply these two together. Root 6 times root 6. Well, it becomes root 36, 6 times 6. And root 36, well, there's actually a value for that. Root 36 asks what times itself. Gives us 36. And the answer is 6. Now, that should hopefully make sense because we're multiplying the root 6 by itself, which is another way of saying we're squaring it. And the opposite of square rooting something is squaring it. They are inverses of each other, and so they're going to cancel out. So it shouldn't be surprising that we get 6 when we're done with it. Okay. So here we've got 2 coefficients and 2 radicals. A -1 and a -1 are going to cancel out and become a +1. And I'm not going to write +1. And then we've got a 2 times an 8. And that's going to give us root 16, which is the same thing as 4. All right, moving on. So we've got some variable coefficients here, a -x times an x power 4, and I might grab a highlighter. I'm also going to focus this guy. Maybe it'll help focus out a bit. I'm going to multiply this -x. You know what? I think we used green when we went over this together, so I'm going to use green for these coefficients. And I'm going to multiply those together first. So it's worth mentioning that this means -x times root x times x power 4 times root y. And it doesn't matter what order you multiply things in, right? So I could rewrite this as -x times x to the power 4 times root x times root y. In other words, getting all my coefficients together and all my radicals together. That's not a necessary step, but just to illustrate that that's really what's happening here. That's why these guys get to communicate in the first place. And we've got -x, we've got a power of 1 there, right? So we multiply these guys, we're going to add their exponents. So you get -x to the power 5. And then we've got a square root, and it's going to have x and y in it. And obviously that's not a radical that can be simplified. So at that stage, we're done. Looking back, I'm not a huge fan of how that looks, because it kind of looks like it's the 5th root. So I'm going to rewrite it as a -x power 5 times the square root of x, y. that in brackets. All right. So here we just have a coefficient and another coefficient, and only single radical. So really, those two only multiply together. So we get negative 24 root 11. And I might check to see if this one can be simplified as well. Now it's worth mentioning, on this first page, we're really just practicing multiplying and using this basic sort of resolving of radicals. So we're not going to have any times when we're really looking for factors that go into 11. Either root 11 can be resolved or it can't. Okay. So same thing here. We've got a 4 and a 2. And they're going to multiply together, so it's going to give us 8. Then we've got a cube root here. Cube root of 6 times 7. So that's another way of saying 8 cube root 42. I'm just double checking here to make sure 16 doesn't go into 42, and it doesn't. 16 goes into 48. Okay, so that's as simple as it gets. Next, I've got negative 3 times, there's no coefficient there, so we'll just have negative 3. And cube root of, and we've got 2 radicands here at 2c times negative 4c squared. All right, so when I multiply these together, I end up getting negative 8 from the 2 and the negative 4, and c times c squared, which is c cubed. Now this is a radical that can be simplified. There are 3 terms that multiply together to give me negative 8c raised to an exponent 3. And that number is negative 2c. Because negative 2 times negative 2 times negative 2 gives negative 8, and c times c gives us c cubed. So overall, we should get negative 3 times negative 2c, which overall gives us 6c. Okay. So here we have a distribution. We're going to multiply 2 by both of these guys. And the 2 simply here is going to give us 4, 2 times 2. And it doesn't really interact with the radical at all because it's a coefficient. Or it's just a regular old number which multiplies to a coefficient. And 2 times negative 5, which is negative 10. And we're done. So, J, you can see, again, we've got distribution. It's multiplying by both of these guys. And so we're going to get a negative, so we're going to multiply this negative 3 root x by 1. So obviously that's not going to change anything. It's just because anything times 1 is just itself. And I've got a negative times a negative. That's going to give me a positive. And that should give me negative 3 times negative 5, so positive 15. And I've got the root of 6 times root of 5x, which should give me root 30x. And that's 6 times 5 times x. Now, in a textbook, that actually might be written like this. They might just change the order to put the positive term first and the negative term second. The reason is, well, I don't know, people might say this is a little simpler, easier to write, is a way of writing fewer positive and negative signs. There's 2 signs required if you write it this way, but only 1 in this way. But this is just as right. All right, another distribution. So I think what I'm going to do this time is I'm going to write this out with an extra step. So I'm just going to not do any math right now. Just going to write 2 root 1/2. And use green for that guy. And it's going to be multiplied by 3 root 8. And then we're going to take away, we'll have 2 root 1/2. And that's going to be multiplied by 6 root 50. Okay. Now, I think I'm also going to rearrange the coefficients so they're next to each other. So I'll do 2 times 3. And we'll multiply root 1/2 times root 8. And we've got 2 times 6, so it's going to be, I'll just write them right now, 2 times 6. And root 1/2 times root 50. Okay, so these guys come together, they just become 6. And 1/2 of 8, well, that's going to be 4. Pardon me, root 4. That's those guys. And I've got these guys, so that's going to be negative 2 times 6, which is negative 12. And this root 50 times root 1/2, well, that's going to become half of 50, which is the square root of 25. Okay, so we're getting there. Now we also have these two, notice 4 and 25 are numbers that show up in our perfect squares over here. And that means they can be resolved. So really that's the same thing as 6 times 2, which is the square root of 4. Take away 12 times 5, which is 12. Take away 12 fives is 60. And overall, that's going to be negative 48. Okay. So things are starting to look a little messy as we get a little bit more complex with some of these expressions. So I've got the cube root of 3 times the cube root of 9. So that's going to give us 3 times the cube root of 3 times 9, which is 27. And we're going to subtract from that. We'll have just a 4 here, because it's multiplied by that 1. And this cube root 3 multiplies with that cube root 1 to give us cube root 3. And that's all well and good, except this 27 here. This guy can be resolved. Cube root of 27 is really just 3. So I've got 3 times 3. Take away 4 cube root 3. And so it's going to give you 9. Take away 4 cube root of 3. And lastly, we have a distribution problem. So I'm going to kind of FOIL these guys out, if you like that terminology. So I'm going to multiply the first term in each set of brackets. So I'm going to call that root A. Maybe I'll color code these. I'm not sure how much this is going to help, so I'm going to give that black. That'll be blue. This guy will be green. And this one will be red. And some of those colors don't pop so much. I'm going to try zooming in and see if that helps a little bit. I think it does a little bit. So maybe I can just adjust this. Okay. So I just want to help you follow along with these. Hopefully these colors will help. So the root A here is going to get multiplied by 2 root A. And then the outside term, so I'm going to multiply root A by 10 root 2. And I've already seen some people use colors themselves as their own strategy for keeping things kind of clean or organized for themselves. So, please try this if you've never tried it before. It can help sometimes. We've got negative 4 root 5 here. It's going to be multiplied by 2 root A. And then lastly, we've got the blue and the red here, right? So that's a negative 4 root 5 times, oops, a little off the page, times 10 root 2. Okay. And now we're just going to multiply these one at a time. So we've got that expression, this guy. So we've got 4 different multiplication expressions in this question. Okay, so we've got 2 times the square root of a squared. So I'll write that as 2 root a squared. And we've got plus 10 root a times 2 is 2a. Negative 4 times 2 will give me negative 8. The square root of 5 times a. And then negative 4 times 10 is going to give you negative 40. And we'll have square root of 5 times 2, which is 10. And that's pretty much everything that can be resolved, except you did maybe notice that that was a perfect square, square root of a squared. These are inverses of each other, so they cancel out, and really, that just gives you 2a. So overall, we get 2a plus 10 root 2a, take away 8 root 5a, minus 40 root 10. And there is our final answer. All right, so I'm going to zoom back out for a couple of questions on the next page. Okay, and on the last page, the first thing we did is we started by writing out all our perfect squares and perfect cubes. So I really recommend you do that, especially on this page. I think it's extra important when we're doing this simplification of radicals. 49, 64, 81, 100, 121, 144. And it looks like we have some cube roots a little later, so maybe down here where they start to pop up, I'll write the perfect cubes. 1, 8, 27, 64, 125, 216, and we'll call it there. Now, this is a situation where I might have a calculator handy. I don't really like those calculators. Well, I guess I'll have to use one. All right. Just in case we're having trouble with our multiplications. Okay. So the first radical is root 8. And we want to ask, well, is there a perfect square that multiplies nicely into 8? And there is. There's 4. There's also 1, but that's not really going to take us any further than we already are. So what I can do is I can rewrite this as a square root of 4 times 2. Now we know from our multiplication rules that I could also write that same expression as root 4 times root 2. And root 4, well, that has a simpler way to put it. Root 4 is just a funny way of writing 2, right? So it's 2 root 2. Okay. So same principle with the next question. We're looking for a number in this line that multiplies into 18. And in this case, well, 4 doesn't work because 4 4s is 16 and 5 4s is 20. But 9 does go into 18. So I can rewrite this as a square root of 9 times 2. And again, I can kind of split that into a square root that can be resolved and kind of a junk square root, stuff that can't be resolved. And the root 9, well, that can just become 3. While root 2 doesn't move, it stays root 2. Okay. So moving on. Here, maybe another step, we've got a coefficient in front, but we'll kind of ignore that for now. And we'll ask, well, can 20 be split into a perfect square and some other factor? And if I look, I see, yeah, 20 can be written as 4 times 5. And 4 is our perfect square. So I can rewrite that as root 4 times 5. And I can keep going. I say 14 times, well, root 4 resolves to 2. And, oops, I forgot the root over there. And that's times root 5. So overall, that's going to give us 28 root 5, because we're going to multiply those two numbers together. Okay. Now, D is a little bit more complex. So I've got a fraction here. And the way I want to think about this is maybe I want to look at numbers that go into 50, perfect squares that multiply into 50, and maybe any perfect squares that multiply into 3. So what I'm always looking to do is write a radical and have stuff that can be square rooted here and stuff that can't be here. And they're going to be multiplied together. Now, in this case, with a fraction, I'm going to write them both as fractions. So 50 can be written as 25 times 2, because 25 is a perfect square. But 3 can't really be broken down, into any perfect squares, so I'm going to just write that as 1 times 3. The 3 is kind of going to be a leftover. Now I can rewrite that. I'm going to get rid of that 1 here. I'm just going to rewrite it as 25 next round. So it's root 25 times the square root of 2 over 3. And root 25, well, that has a solution. It's 5. 5 root 2/3. Okay. So let's keep going. Now, I'm going to solve this question 2 ways. So the first thing we're going to do is I'm going to just sort of start from the top. Pardon me. So I can see that 4 is a number that goes into 32. So what I can do is I can say, okay, well, that's negative 3 root 4 times root 8, right? Now, you notice what I did there is actually I just skipped this step because I think we've done a few of these now, and so I'm just going to jump straight to writing the nice radical that can be resolved and the other thing. All right, so it's going to become negative 3 times root 4 is 2 times root 8, or negative 6 root 8. But then, if I'm looking closer, I might notice root 8 can also be written as a product of a perfect square. So I've got negative 6, and I can say is root 4 again times root 2, or negative 6 times 2. So that's negative 12 root 2. I skipped another step there. Okay, so that's fine, but that required 2 steps. What we did is we recognized that 4 was a factor of 32 twice. So if 4 is a factor of 32, 4 times 4 is also a factor of 32. I think I might have said the wrong thing there. I just want to repeat that in case I did say the wrong thing. If 4 and 4 are both factors of 32, then 4 times 4, or 16, is also a factor of 32. And it is, because 32 can actually be also written as 16 times 2, which is to say negative 3 root 16 times root 2, and root 16 is 4, so it's negative 3 times 4 root 2, which is negative 12 root 2. Either way, so I guess the point here is that it doesn't really matter if you saw the biggest perfect square. You can kind of just start with whatever number you can see that goes into 32. However, the shortest route is always to find the biggest number that goes into your radicand. All right, so with this question, I might look, and I'm going to try to check to see what the biggest number is. So maybe I'll look at 72, and does 4 go into 72? Actually, I'm not perfectly sure, maybe. So I'll just double check. 72 divided by 4. Oh, it's 18. Okay, so actually 4 works. So I'm going to put a tick next to it, but I'm going to keep going because maybe there's a bigger one. So 72, does 9 go into 72? And that actually, yeah, it does. I know that because 72 is 9/8. So that one also works. What about 16? And again, I'm not perfectly sure. You don't have to have all of this worked out. And you can take your time to just double check. And, well, it doesn't quite go in nicely. 16 goes in 4 times plus half of another 16. So not 16. 25, well, it's pretty easy to know my multiples of 25 because we deal with money a lot. So we skip 25 and we go from 50 to 75. What about 36? So what's 72 divided by 36? Oh, okay, so 36 also goes into 72. But Now that's half of 72. So I know that none of these numbers are going to go into 72 because this already represents half. So I can rewrite this as root 36 times square root 2. And that's the biggest root that goes into, the biggest perfect square that goes into 72. So I can call this 1/2 times the root square root of 36 is 6 times root 2. That's going to become half of 6 is 3 root 2. Okay. So I can do a similar thing here with root 200. So there's a lot of these numbers that actually go into 200. 4 does, and 25 does. But 100 is for sure the biggest perfect square that multiplies into 100. So I could also write this as negative 6 root 100 times root 2. And it's going to give me negative 6 times root 100 is 10. So it's going to be negative 60 root 2. Okay. Now, again, we have one of these fraction questions. So we're trying to split 125 over 72 into some big fraction that can be square rooted times some big fraction that can't be. So I'm going to first ask, what is the biggest perfect square that multiplies into 125? If I look, I can see 25 is going to work. 25 times 5 is 125. And for 72, well, we just dealt with 72 over here. We saw that 36 went into 72, and 2 didn't. Okay. So then I'm going to write this over here. I want to give myself a bit of space. So negative 4 over 15, square root of 25 over 36 times the square root of 5/2. And so that'll become 5 over 6 when I finish square rooting. Equals negative 4 over 15 times 5 over 6 root 5 over 2. And then lastly, I'm going to multiply those fractions together. I might zoom in. I'm running out of space a little bit here. Probably could have done that on another piece of paper. All right, so these guys, I can see a 5 common factor between 15 and 5, so it'll be a 3. And I'll divide this one by 5 and leave a 1. And I can see a common factor of 2 here, so I'm going to divide them both by 2 and leave 2 and 3. So overall, that's negative 2 over 1 times 3 over 3. So it's going to give me negative 2 over 9 root 5 over 2. Okay. Now I've got a cube root of 16. So I might be tempted to want to just say that's 4, but of course it's a cube root, not a square root. I can zoom out a little bit here so I can see the cube roots and work on this problem. So, but I can see that 8, which is a cube root, multiplies into root 16. So I can say that's the cube root of 8 times the cube root of 2. And the cube root of 8 is just 2, right? So it's 2 times cube root 2. Okay, so I can do a similar thing here. I actually know that 8 also goes into 32, and then it must go into negative 32. So what I could say then is this is the same thing as cube root of 8 times cube root of negative 4, or I could say it's cube root of negative 8. Get that negative on the outside of my radical. And just a cube root of 4 here. And so that's going to give us negative 2 times the cube root of 4. And so we could have left the negative 4 inside the radical. Nobody said, there's no real rule that said we had to bring the negative out. But it is simpler to have that negative on the outside of the radical. It helps us see that it's on the other side of 0 on the number line. and definitely know that it can be resolved in some way, whereas maybe some other negative radicands can't be. So it's easy for us to see without thinking too hard. Okay, for 250, we might see that 125 is half of $2.50 is 125. So I could call this cube root of 125 times the cube root of, say you didn't know, right? You can just check, right? How many times does 125 go into 250? Oops, sorry. And the answer is 2. So it's going to become the cube root of 2. There's a lot of root 2's and cube root 2's in these questions. The reason for that is because they often keep pretty low numbers while having some higher perfect cubes and perfect squares. Anyhow, cube root of 125 is 5. We have a cube root of 2 to finish us off. Okay, I wonder if I have enough space to do this question. You know, I think I might. Okay, so again, we're going to want to split this into a fraction with things that can be resolved out of a cube root and cube rooted and things that can't. Now, on the numerator, I can see that really the only factors of 7 are 1 and 7, and so I can really just write them like this. I can't take it any further. 8 is too big. Okay, for 270, I can see that, well, 27 definitely goes into 270, right? That's 27 times 10. Okay, so the whole thing can be rewritten as cube root of 1 over 27 times cube root of 7/10. And if I cube root that, that's really going to give me 1/3. This is 1/3 cube root of 7/10. We put equals there to make it a little separated. Okay, moving on. So say I'm not sure what of my perfect squares goes into 128, pardon me, my perfect cubes. I'll just say 128 divided by 8, and that's going to work for me. But actually, there's a bigger perfect square. Sorry, it's been a long week. There is a bigger perfect cube, is what I meant to say, that goes in 128. We can check 27, but it isn't 27. It is 64. So that gives us 2. So we can actually say this is the same thing as 7 times the cube root of 64 times the cube root of 2. All right, and so I know the cube root of 64, but that's just 4. And I'm left with this cube root 2, so it's the same thing as 28 times the cube root of 2. Another cube root 2. Okay. Oh, shoot, I forgot the negative here. Negative, negative, negative. Oh, that almost cost me a cookie. I'm going to put a box around this so it's a little messy, but so I don't get it confused with other things. And yeah, that's not a very clear negative. I hope that comes through in the scan. Okay. 81. So 8 doesn't go into 81 because 8 only goes into even numbers. But maybe 27 does. So I'll just check with my calculator and check. Oh, 81 divided by 27, and it does go in 3 times. So that means I've got negative 2 cube root of, I'm going to take the negative out as well, so negative 27 times, I've got the 3 left over here, so we're going to leave that 3 here. Okay, and so I've got negative 2. The cube root of negative 27 is, well, it's negative 3. And I've got this cube root of 3 left over. So the last thing I might do is multiply these together. Negative 2 times negative 3, that's 6 cube root 3. Okay, so we're going to move on here. So as we go through, really this becomes a skill of just recognizing which of these numbers goes into these guys. And I can see 125. We'll go into 375. So it's really the cube root of 125 times the cube root of, that turns out to be 3 125s. And so it's 3/5 of 5 times the cube root of 3. 3/5 of 5, if I multiply those, that's a fraction, I can divide both of these by 5. 1 and 1, so actually it's just 3 cube root 3. Okay, well, I think this number turns out to be kind of interesting. I'm going to put a little dash here and say, okay, so I've got 3/10. And I'm going to separate this into a fraction that can be cube rooted and a fraction that can't be. Now, it just so happens, if 1,000's come up a few times, 1,000 actually is a perfect cube. So I'm going to say 1,000 times 1. And 81, we saw earlier, was 27 times 3. So the more of these you do, the more you see these patterns. There's only so many variants of multiples of these numbers. All right, so the reason this is interesting is because we get 3/10, and the cube root of 1,000 is 10, and the cube root of 27 is 3, times the cube root of 1/3. And when we multiply these through, the 10s cancel out and the 3's cancel out, leaving 1. So we actually just get the cube root of 1/3 when we're done. All right, how are we doing for time? Well, this video is about time to almost be done. Just going to pull this up because we run out of time pretty quick on these things. So, all right. Lastly, I've got some variables to play with here, and I've got a cube root, square root of b cubed. So what that can be simplified to is the square root of b squared times b, right? Where this one can be square rooted, and this one can't be. And the square root of b squared, well, it's just b. So b root b. Okay, now we've got a square root of, so we got the variable and we got the coefficient. So I'm going to say 28. Let's take a look at my perfect squares. And I can see 4 goes into 28 7 times, so I can call it 4 and 7. And I'm going to leave some space for the variables, and that's going to be m raised to power 4 times m, because that's the highest power of m that I can square root. And there's an m left over there. So it's going to give us square root of 4m raised to power 4 times square root of 7m. And overall, it's going to give me 2m squared root 7m. Okay. So again, when we have these fractions, we're going to want to separate them to fractions that can be simplified and fractions that can't be. And 16 times 1, I can see on the bottom, is going to work out. Now 45 can be split into 9, a perfect square, and 5, a prime number. And c can't be square rooted ever, so c is going to stay here. But the d squared can come out here because it can be square rooted. And we're just sorting. We're sorting things that can be square rooted and things that can't. We get -3, and this all simplifies to 3d over 4. And this root just becomes 5c because we don't have to write that we're dividing by 1. Okay, and then when I multiply these together, I get negative 3 times 3, which is 9d over 4 root 5c. And the reason it becomes not, it doesn't become 90 over 12 is because this guy is a fraction over 1, so we multiply the denominator is 1 times 4. So that 3 doesn't multiply by both of them, in case that wasn't obvious. Okay, and last one. So again, we've got some numbers out here, and we're going to split this into a radical that we can square root. So 9 can be square rooted, y squared can be square rooted, and we're going to have to break z into its components. If I bring out the power 4 of z, that's the highest power power of z that we could square root, leaving us with actually just a z left over, because z to the power 4 times z is z to the power 5. Okay, so that gives us z over 3y times square root of 9 is 3. The square root of y squared is just y, and the square root of z raised to an exponent 4 is z squared. And we have this root z left over, one guy that couldn't be simplified. And of course that's all over 1. So when we multiply these, the 3's cancel out, the y's cancel out, and we're left with the z times z squared, which is z cubed root z. All right. Now you have answers for the Michelson questions in the back of the textbook, so I encourage you to check there for the answers to those questions. And please let me know if you have any questions or don't understand how some of those are done. Good luck studying, and have a great long weekend.